You are starting your career in structural engineering and you want to design a building just like this. There is one formula which comes everywhere, and it is the core of structural design. That formula comes in steel design, concrete design, masonry design, basically comes everywhere. That formula is moment capacity, which is the reduction factor into yield strength into section modulus, which is nothing but moment capacity, which is again stress into section modulus, and also comes into footing design, beam design, column design, and many more. To understand this, we have to understand the area moment of inertia. To understand this, we consider two lines, x-axis and y-axis, and then consider an arbitrary area. Consider a small area dA at a distance of y from the x-axis. The area moment would be y into dA. The moment of inertia of the small area about the x-axis would be y squared dA, and the moment of inertia of the whole area about the x-axis would be integral of that, which is y squared dA, and the moment of inertia of the whole area about the y-axis would be Iy into x squared dA. Remember this formula. Now let's understand the area moment of inertia of a rectangle. Consider two axes, x and y. Consider the rectangular section of height h with b. Consider a strip of height dy. Look at it about a distance of y from x-axis. Area of the strip is b dy. Moment of area of the strip is y squared b dy. Moment of inertia would be ix y squared b dy. Considering from minus h by 2 to h by 2. We got here, solving the definite integral, we have ix equal to bh cubed by 12. So remember this. Now consider a beam of uniformly distributed load. AB is a neutral axis, and then CD is the line below the neutral axis. Let's be C and D be y from AB. We have a radius of curvature r. The length of segment AB is r theta, CD is r plus y theta, and we also know strain equal to change in length by original length, which is equal to CD minus AB by AB. Equating that, r plus y theta minus r theta by r theta. Solving this one, we get strain equal to y by r, and this is called bending strain. We know that from Hooke's law, stress is directly proportional to strain and stress elastic modulus into strain, and then from this formula we get Ey by R. That is called bending stress. Remember this formula, guys. Now let's see the formula that we have derived before, starting with moment of inertia, and then comes the bending strain. Let's check out the moment capacity, how it can be derived from the formulas that we have seen before. That is bending stress, which is equal to Ey by R. For that, let's consider a simply supported beam under gravity load. We know that the section above the neutral axis goes in compression, and below the neutral axis goes in tension. Let's consider a small strip at a distance y from neutral axis. We know that force equal to stress into area, which is sigma into dA. Moment force equal to force into distance, and also if we integrate it, we get sigma dA into y, and arranging it, we get y dA, and then putting it inside, we get y squared dA, which is E equal to r by y. We get that from the bending stress formula, and then we get, substituting that, we get Rx by sigma y by into r. Moment equal to x, sigma y, which is sigma equal to my by I. We know that z equal to I by y max, and substituting that, we get m by z. The relationship between the bending moment, bending stress, and section modulus is everywhere, guys. You really need to understand this. This is for the bending moment capacity of steel beam from the Australian Guidebook for Structural Engineers by Leon Pack. And then if we look at different book for pre-stress concrete, this formula we can find it here. Moment equal to section modulus into stress. And then for masonry also we can get it moment equal to bending stress intersection modulus. We can even see it in the footing. If you see the formula very carefully, 6m by BD square, which is m by z, and also we can find it in Australian concrete code. Guys, if you enjoyed this video, please like and subscribe.